Good morning, everyone. Really glad to be here. Like many of you, I was commenting to someone my last in-person, at least a big conference, was Census in 2019, and lots have changed in the field since. My own interests evolved as well. So this talk is really not so much about something mature that we have done and all, far from it. It's more of a, kind of some things that in recent years have begun to sort of at least interest me. And a lot of it is driven, frankly, by changes that have happened within IoT. So Falco mentioned that I've been working in this space quite some time, and indeed that's the case. And actually this year I completed 25 years at UCLA, so quite old. Within that time, I mean, when we started out with sensor nets and things like that, what was happening was what I would like to call as traditional IoT, namely very simple sensors. Those days, if you go back, look at the software stacks, what you were doing, monitor temperature, do this, some threshold it, take some action based upon that. So relatively simple data. Even if there was any sort of more complicated data type, using very simplistic methods, we would get to some sort of structured data and work off that. So the machine learning and models at that time were either very simple machine learning methods or, for the most part, what I would like to call as first principles type models, those where we exploit DSP, physics, things like that. But fast forward, if we look now, again, I don't know about this conference, but I recall in 2019 census, my thought was that, gee, I mean, almost every session was in some shape and form was about applying deep learning methods or at least sort of, I have sensor data, I'll learn a model, and I'll report the result category of papers. And I think we are very familiar with it. It has done wonders for our field. And certainly in terms of capabilities and accuracies, they are kind of in a different category than what things were in the past. Now, driving this, of course, are a variety of trends that sort of have been with us. First and foremost, sensors and actuators that we work with have changed. Instead of the very simple sensors which were measuring things almost close to what we were interested in, right? Things like temperature, location, stuff like that. Now we measure things, but then we are interested in inferences which are quite far from it, right? From extrometry data, gee, is someone stressed or not? Those kind of things, right? A huge gap. In many cases, inferences that we can't even know the physics of. And of course, driving that has been the use of neural networks, and in turn, enabling us from, in using these neural networks have, of course, been the very same hardware, which sort of initially made things different in sort of big computing, but now with efforts like TinyML and all, we're seeing lots of accelerators and all, which are really targeting our IoT devices of different capabilities, sort of smartphone, and all the way down to kind of really low resource, ultra low resource type devices. And this change has resulted in a couple of different sort of impacts on us. One is from very simple sensors, but with sort of huge amounts of data, we are able to make inferences which previously we didn't think were possible. I think every time I look through proceedings of one of our main conferences, I see, gee, I didn't realize I can make this inference from this simple sensor. And so people, in some senses, we have suddenly discovered a tool which, at least in an ad hoc manner, is letting us discover or at least computationally model the physics behind lots of inferences that we are after. So variety of human behaviors, that's where my initial interest started in this. I mean, going back a decade or so ago, transportation modalities and other types of human activities and all. lately in our community, a lot of cool work on using these for interaction, more deeper type of behaviors that affect our health, for example, as well as even sort of, in many cases, kind of replacing methods where we had well-established physics, control, signal processing type methods, but neural networks have again sort of let us model physics we couldn't. A great example is tracking, for example, where drifts in sensors had always plagued sort of accuracy. So now suddenly, even whether you're tracking using IMU or whether you're tracking in a video, we suddenly are able to see performance which previously were just not the case. And the other thing which has happened is that, and this is particularly relevant to our field, that unlike kind of the mainstream work which is going on in ML and AI, where much of the focus is on video and NLP and modalities like those, people are applying those kind of models in context of RF signals and LiDARs and sort of other type of sensing modalities. And so our ability to, what sort of, at least in this country, military-oriented applications like to call it situational awareness or situation understanding, we are now able to do sort of much deeper type work. Tarek is leading a big effort in this called Internet of Battlefield Things, and as part of that, we have been pushing the envelope quite a bit in terms of what we can infer about the scene. No more is it simply a camera looking at a scene and saying, hey, there is a car here and all. Now, by fusing it with other sensing modalities, we can say, oh, that faraway car, is the engine on or off? If there's a room full out here, we can say something about the vital signs by combining 3D imaging with RF sensing. So there's a lot of interesting capabilities that we couldn't imagine even a small number of years ago. And sort of at a macro level, there's certainly a class of applications that are emerging, whether it be health-related, or I heard one of the talk is about digital twins, so digital twins of complex spaces, so that then we can make decisions using them, or building controls, and I think an area that I've sort of focused in recent years quite a bit also is underwater sort of health of ocean and animals in oceans, these kind of things. So again, inferences that we can make sort of enable all these kind of applications. So obviously a lot to celebrate in some senses, and I'm sure MobiSys probably will have a share of papers applying DNNs and to sort of make various kind of inferences, essentially helping improve our systems, right? But a lot is missing also, and I'm going to highlight 3 things. 2 of them I'll just mention, but really sort of the main one I'm going to focus on is the third one. So kind of the 3 that highlight and which at some level sort of I care quite a bit about. So one is, in this rush to collect data, create models, and report the results, I think we've kind of forgotten that what about the robustness or the adaptability of these things to novel situations. One of the advantages of the classical first principles methods was if something changed, because we had a deeper, the model was based upon our sense of physics, we could change the parameters. Just to cite an example, we've been using methods like deep reinforcement learning quite a bit for control type settings. Now in classical control, if you change the sample period, how the parameters change was relatively easy to figure out. But if you have a deep RL model and then something about the environment changes in that fashion, then you have to relearn, right? So we replaced tweaking a parameter with kind of retraining, and that's complex. Second one, again, even though these methods help a lot in terms of the performance, but in very resource constrained platforms, the implementation still remains a challenge, so the embedded implementations part. And the third one, and this kind of circles back, so in some senses, DNNs brought up these advantages, but sort of gave up some. And so I would like to argue that perhaps at this point, a rebalancing of data, knowledge, or neural versus sort of first principles methods is needed. So on the first 2 points, just some quick thoughts. So as we have been doing these systems, we have encountered sort of variety of ways in what sort of in mainstream AI ML people like to call as domain shifts. Domain shifts usually in those disciplines have a much narrower implication than I think in IoT that we end up facing. In some applications, we find immense person-to-person variation. I mean, unless you're a big company who can afford to do a few 100,000 people type studies, a typical sort of application-specific deployment and all, you'd be lucky to have a few hundred type sample size. And most academic studies reports results on a few tens type things. And the moment you attempt to apply them outside that population on which you train, huge things happen. Essentially, person-to-person, in the applications we are in, person-to-person variations swamp sort of things that you see, the kind of distribution changes that you might expect otherwise. So unfortunately, simply acquiring new data is not solution either, because one of the things that distinguishes IoT realm, sensing realm, is that we can't retrospectively sample, usually. Mostly because we are dealing with sensing modalities for which we don't have human counterpart, so we can't just crowdsource a year later, and a cat in an image remains a cat a decade later, but my accelerator waveform, whether it was for walking or running, I can't tell you even 10 minutes later for this kind of data. Deployment settings are quite different. Our sensing substrates are quite dynamic. I think currently the norm is when we design these things for a particular family of sensors, even if the modality remains the same when we change the sensing substrate, either because our lives are pretty volatile, right? I mean, sometimes I have my phone in my pocket, sometimes it's not on me, and then it's my wristwatch, other times on my bed, it's a different set of sensors. Our ability to make the inference while the underlying substrate is fluid, and then, of course, the additional issue that we all are different. So again, sort of generalizing across this heterogeneous and fluid sensing substrate is another form. We are increasingly combining data from many sensing sources, different devices, and we're realizing that misalignment in their respective notions of time and also notions of location plays havoc with the accuracy, even in the stages where if you're collecting training data. There's some excellent work out of my collaborator Santosh Kumar's group at Memphis where they show that there's a lot of temporal uncertainty in the labels themselves. So again, something to worry about. We can't scale our systems if the labeling process is onerous and error prone. And likewise, platform level uncertainty. Our platforms IoT platforms are increasingly multi-tenant, as in we are running different things on it, and of course they also adapt to changing energy conditions and such. So the performance they provide, for example, the latency they provide, they change, and as long as you were doing open loop inferencing, it didn't matter. But as we are doing closed loop, sort of going from sensing to action, then these things begin to affect the actual application performance. On point number 2, embedded realizations. So what we have seen is that there's huge promise in applying DNNs over simple physics-based methods, and tracking is a great example. There's a very mature history of sort of what I've been referring to as physics-based or first-order, first principles methods. So DNNs improve things quite a bit, mostly because our sensors have lots of hard-to-model physics drift in this particular case, but the same thing applies to other sensing modalities. And yet we are trying to put these things on devices which are still, I would say, 1 to 2 order of magnitude different from the models which currently are there. In this particular case, on the right-hand side, the first two are the first principles methods, very lightweight, but much higher errors. And the third one, so in this field over the past 3 or 4 years, deep neural networks have emerged as combating the drift problem, but at a cost which may work for your smartphones, but not for your little microcontroller class devices, certainly not in terms of memory. And that's part of our devices that is not improving that rapidly. If you go back to roll back 15 years, the platforms we were using versus the platforms we are using now on the tinier devices, they have improved quite a bit on clock frequency, but not on memory that much. Okay, so rest of my talk, I'll kind of focus on kind of the third point, and in a way, it kind of relates back to that perhaps we need to rebalance the first principles and deep neural network type approach. So, so DNNs certainly have helped a lot. One thing I would like to mention is that the realm at which they have excelled quite a bit are what I would like to say, making rich inferences over very short time span, short time windows, right? I mean, is someone stressed or depressed or kind of am I walking or running? These are short time window type events and things which we couldn't do previously because really we have no understanding of the physics of these things, but we can kind of do that now. But on a couple of things, they fail miserably. And one is this whole issue which some collaborators of mine like to call as the issue of tellability and explainability. Explainability, we all know, Falco kind of referred to that also, which is in many of these applications, not only do we want good predictions, but at least we are, for a variety of reasons, we also want some explanation on what happened under the hood. And I'm sure many of you have probably followed the literature on explainable AI and interpretable AI and things like that, and that's part of it. In our realm, it's also about we need to be able to certify if things go wrong, audit, so there are more reasons behind being explainable than sort of what is normally the case. But the flip direction is also equally important, and that's the tellability dimension, which is there's a lot of background knowledge which at the very least can help with the problem that we have relatively hard to acquire labeled data, and while unsupervised methods help, but so can human knowledge in many domains. We have sort of reasonably good models of the physical world in some cases, so that could be kind of the starting point. But even more importantly, our IoT systems operate in context of the human society and therefore have to follow rules, regulations, norms of various forms, and how do we get that information into our systems? So that remains part of the thing, and more generally, all sort of other background information. So this back and forth with the humanity or individuals and society and sort of governments and all is pretty critical, and currently we really don't have a good handle on it because our approach really is collect data, try to collect labeled data if we can, otherwise nowadays sort of unsupervised methods becoming popular, and then create a model and deploy, but we kind of miss out on a lot of these things. The second part, which sort of goes to something I said a short while ago, which is these things excel at what I like to refer as simple events. But in many cases, we are interested in more complex events, events that require us to connect the dots between things that sensors may be observing, far apart in time, far apart in space. I have sort of some examples out here, like unattended bag. It's not simply a snapshot of a thing, right? I mean, maybe the person just quickly went away and will come back. So you have to examine these things over time, and also in space. Someone puts a bag on a platform and then walks out, so now you're combining things from two different sensors. Or in a hospital setting, nurse violating sort of hygiene protocols. These are things which may happen arbitrary amounts of time apart, and one has to somehow get a handle on that. So this is where we excel, right? I mean, we as humans, because of our ability to look at the big picture context, long spans of time, long spans of space, we are able to reason our way through. This is something, with a couple of challenges we face. One is we don't have huge amounts of data for such complex events. So our traditional method, let's collect these things and train our model on it, doesn't really work. We excel on it because we are operating in context of kind of the rules of our society, which train us on certain things. So that reasoning ability that we bring to bear on that. So some other examples, imagine you're a restaurant and I'm sure you have seen these signs, employees wash your hands, things like that. There are good ways of using the restroom and unhygienic ways. We want to be able to detect these things. Again, kind of more complicated things, a lot more permutation. You can't simply apply methods such as, let's say, if I'm classifying sentiment of a document using some topic modeling kind of an approach, here the sequencing matters, right? It's not simply the presence of some aspect in a particular longer sequence, but really the order in which they occur, how many times did they occur. All these kind of issues matter, and they have to be precise. There's a big difference between flushing followed by washing your hands and the other way around. So sequence and all plays kind of a big role out here. So picking on sort of this nursing example a little bit more, in this particular case, the nurse cares for one patient and then much later potentially cares for another patient and forgets to sanitize, do the wash the hands and stuff like that. So in this particular case, our traditional sort of approaches kind of begin to fall apart. And in particular, I want to point out that when you look at it, your first reaction would be, hey, but isn't that what LSTMs and time convolution networks and all do? And true, and the newer transformer type methods and all. One thing I would like to caution is that, even when you look at these networks, the context window that they look at is fairly limited. It's of the order of what they kind of refer to as sort of the effective context length is relatively small by our standards. It's good enough to capture a few paragraphs, but we are talking about sensors which are at higher sample rates and things like that. So it essentially translates in our case in windows of like a few seconds. And which is why when you look at sort of so-called complex activity type benchmarks and all, they're few second clips. Whereas the kind of complex events we have to face in IOBT setting, in hospital setting, in restaurant setting and all are much longer. So I've given sort of the kind of time windows, the kind of memory our deep neural networks have, and they're relatively puny relative to kind of what our needs are. Essentially, like I said, the state-of-the-art stuff would be order of, let's say, a few hundred to a very, very small number of thousand samples, which is nothing relative to what we kind of need to have. Now, there exist systems for detecting complex events in industry, particularly in spaces like data center management and things like that, in database, if you go to conferences like SIGMOD and VLDB, but they kind of operate over structured data. They are already some sort of structured metadata. Usually these systems may use SQL or some sort of other formalisms like that to describe sort of complex sequences. They work great for that, but this always already presumes that someone has taken care of all that work of it. Our needs are to be able to do complex events over raw, natural, unstructured, noisy, messy kind of sensory data. Also, sort of methods like hidden Markov models or such, again, don't work because they come with very strong assumptions on what a complex event even means out there, okay? So again, a lot of like Markovian assumption in that case sort of kicks in and all. So these systems don't sort of cut it either. So what's going on out here? So on one, some of these things I've talked about, being able to explain, incorporate knowledge, these kind of things are done pretty well in kind of the first principles domain, or what in AI world would be called as the symbolic AI domain and all, right? I mean, the flip side though is, there's a reason we sort of the AI field moved towards ML is because they are computationally painful, they don't handle messiness of the data that very well, and particularly for the kind of inferences we are interested in, right? Where the sensors are not directly measuring what we seek to infer, these methods are pretty weak at. On the other hand, data-driven models excel there, but then I kind of highlighted their weakness. In some senses, sort of what I'm arguing for is we need to sort of find a way to sort of combine the two, bridge the two in some manner. And a little bit akin to what we do, what Daniel Kahneman calls as system one, system two kind of things. But essentially, some things are for good perception. Clearly, what we are currently have been doing in recent years is excellent, but for a lot of other things, perhaps bringing back some of our first principles approaches would be kind of useful. So thanks in collaboration with sort of folks, partly some from Army Research Lab, some from Air Force, some from Cardiff University and Imperial College in UK. We have been examining some of these things, right? I mean, what would this marriage of these two domains look like in our particular context? And our first stab at this was kind of a very straightforward attempt at it. Let's consider a two-part system where the raw data goes into kind of neural networks, which are extracting some sort of concept, some sort of simple events out of it. And then there is a symbolic layer, a logic layer, which we express using some sort of a pattern rule or some sort of a set of logic rules, probabilistic. And this allows us to both inject human knowledge, which is background knowledge, as well as the way we stitch together the simpler events over space and time. And that gives us a complex event. And even with this, you begin to face an issue that if you make most of the things on the logic side, on the logic module, then you begin to lose advantage of computational efficiency and things like that. So even if you're hardwiring a system like that, it's important to, it becomes important to kind of design these things properly. And we kind of spent a fair bit of time. One of the things we focused quite a bit on was, could we propagate uncertainty? So one of the advantages of neural networks is that when we get some inferences out of it, it's not simply we're getting the prediction, but we also have increasing framework which let us reason about the uncertainty behind it. Could we propagate that through the logic layer and then talk about uncertainty of the complex event, uncertainty of time, location, and the type of complex event? So we kind of focused on that. Fortunately, in sort of now there are some pretty good probabilistic logic type frameworks also, so we can kind of marry the two, but nothing comes for free, so there are computational issues that come into that picture also. We spent some time defining ways in which the user can easily express the complex events that are of interest. So in a military setting, for example, these are the intelligent analysts. In other cases, the query you ask that gets translated into a formal sort of underlying complex event. And in our first system, sort of the underlying implementation was a finite state machine, but in other cases, you can imagine a logic inferencing kind of a framework, which our collaborators kind of use. So essentially the kind of stuff that good old Prolog type systems used to do. declare a bunch of assertions, which are your rules, and then you validate as your data in a given time window is satisfying that. Well, so if it was simply the inferencing part, it's okay. The problem that we face is that, again, these systems need to adapt to novel settings, to domain shifts, to changing rules, to changing types of data, so a variety of sort of reasons. It's not enough to simply sort of hardwire, take pre-trained neural networks, slap on a set of logic rules, and then deploy it. You have to sort of fine-tune it. So while data about complex events is hard to collect, but it's not entirely absent. And again, in a setting where you might, if you're going from sort of one deployment to another deployment, there may be changes in the tactics and the procedures and the rules of the game, and those need to be defined. Your terrain, building, or the individual, they may be different, so your perception layer has to be modeled as well. And some other sort of concurrent work has also sort of observed these things. So there was one paper from Ramesh Govinda's group at Census 2019, which was looking at certain kind of complex events in context of cameras observing an urban scene, and they had noticed kind of the same thing, that there is a, while the rules in some senses act as a filter, so that you can reason robustly in presence of uncertainty, perhaps, but your underlying perception layer, its performance does matter. So what it means is we got to be able to make use of the data that we have and do some end-to-end training, even though now we have this hybrid architecture, neural network followed by rules. Now we know how to incorporate new data into purely neural setting pretty well, right? We freeze some layers, we fine-tune the other layers, transfer learning, and sort of other such methodologies that have emerged in recent times. Could we do the same thing out here? Now, the problem is, as we normally think of, like, hey, there's a program or a set of logic rules or a state machine, we can't really sort of go through that. What does it mean to backpropagate across that? So one of the approaches that we did, with some support from literature that has emerged in recent years, is that could we create a neural proxy? So there's this concept of relaxing a program into a neural network or distillation process. Think of it like imitation learning counterpart, except that what your teacher in this case is the state machine or the logic rule set, and what you're training is kind of a neural network. So the approach that we explored was, what if we were to use the logically expressed reasoner, that module, and use that as a teacher to then train a proxy neural network. And for the training phase, that we keep that proxy neural network fixed, but that now lets us sort of train the whole pipeline. So if I have additional data, let's say I'm deployed in a new building where there are some changes in terrain and all, I can now begin to kind of fine-tune my neural layer through this thing. You could even imagine that if there were some changes in kind of the knowledge in the rule side, we could also let the neural layer evolve. And I'll mention later that I think now, because of a variety of work which has happened, not by us, but there's pretty fluid back and forth between neural world and symbolic world. I mean, in some senses, they're just two faces of the same underlying reality. So we can play this game sort of quite well. So this system, Neuroplex, which we did, I think we presented it at Census in 2020, sort of took this approach of starting with a system where human knowledge was injected, but then sort of going into an all-neural system so that we can fine-tune these things, and then revert back to the human knowledge kind of system. So in the inferencing phase, it kind of just acts as a hybrid system. In the training phase, it sort of plays this game of proxying into the neural work, does the back propagation, and then works of that. So variety of things that we encountered in this. One of the questions which obviously comes up is we are approximating in the neural world, so we certainly are not explicitly representing the rules that may exist accurately, and therefore some error can creep in through that. There are also computational issues that come. I'm going to skip a few of these slides. But what I want to point out is despite these sort of very valid concerns that one might have, in practice, this approach worked out fairly well for us. I'm presenting 3 simple examples, but we've also applied it into more complicated military type settings, which I'm going to spare you. But there are 3 sort of benchmarkish kind of stuff that we used. One is detecting events over a stream of images. I'm using MNIST as an example out here, but concept kind of applies in general. So essentially, I'm looking for certain kind of objects appearing in a particular temporal or spatiotemporal in some of our sequence in that space. Another one we looked at was complex acoustic events, where sort of the audio streams, and we are looking for certain patterns there. Like, for example, we had whatever, children playing, then suddenly a gunshot, and so kind of the usual urban type things. And then the nursing activity, which I have been sort of mentioning before. What we saw is, so our kind of baseline in these cases was the all neural approaches, the kind which sort of we would apply today. And generally, we found that on the metrics that we started out with, which is we do better in accuracy, we are more data efficient, as in as the amount of complex data are available, we become better. One thing, again, to bear in mind is that it's very painful to train by collecting data which is both simple events and the complex events. It's relatively easier for us to say, oh, the nurse violated the hygiene protocol. It's much harder to go around and ask someone to label each and every segment where the atomic event happened and start and end and all. So that's where we begin to excel, that if you give us corpus of data where the complex events are labeled, and we are able to sort of make effective use of it, whereas without sort of atomic event level information, DNN type systems fail because there's just not enough information for them to do stuff meaningfully. We also do very well as we increase the context length, which is where we kind of started out with. We are interested in events that may transpire over tens of minutes or hours, as opposed to just a few second window. And kind of the bottom table is our attempt to kind of evaluate that. So at least from this kind of initial systems that we have been playing with, things look promising. Promising enough that I noticed in the past 2-3 months, there have been several calls for proposals out in this country from DoD, some of which cite our work, looking for ideas in this space there. So I think there's it was heartening at some level. I mean, I think we have just taken some baby steps, but I think beginning to look at that IoT systems are long-lived systems, and they're not simply about what's happening at the moment, but really reasoning about what is happening on a longer time scale. Now, this proxy approach is one way of looking at it. You could also ask the question that, what about, can we make the logic itself differentiable? And around the time we were doing this work, there were actually, after we did that work, there were some in the main AI community, also there were ideas beginning to emerge in this direction. So today the reality is that there are some systems which allow you to have differentiable logic. Essentially, the way they work is they take your logic rules and they map it into an arithmetic circuit, which is differentiable. And now, and it can have parameters. So like if your logic rules are probabilistic, then they appear as parameters in that arithmetic circuit. So you can think of it as just like a neural network, you have another network which happens to be parameterized and differentiable, and now you can play this game through that. So one particular system appeared at NeurIPS 2020 by some folks in Europe. So it builds upon a system called ProbLog, which is one of the more popular probabilistic logic system. This work introduces neural predicates into it, DeepProbCEP. I've just captured some figures from their website because then in subsequent work, or rather my collaborators, they kind of led this part. We ended up using that approach. So kind of the idea now is, instead of taking a neural proxy, we express the logic module using a probabilistic logic, which is differentiable, so we can kind of go entirely end-to-end without kind of approximating it. So it has the advantage that we are not compromising on the integrity of the rules, right? Because our student-teacher type approach, where we were doing the neural proxy, can, in principle, take that hit. The other advantage of this kind of approach is that if there are parameters in the logic layer, right, I mean, you can leave some probabilities in there and all. Now, in an end-to-end setting, you can learn those parameters also. So two big wins, right? I can learn the logic rules to some extent, and I can not compromise on the integrity of it. But again, like in much of engineering, nothing comes for free. So the challenge is that part of the reason we tend to be attracted by DNNs is that computationally they are so great, right? And I mean, they are tensorized, we have accelerators, so beautiful in terms of computational complexity. And indeed, we see that between these two versions of our system. So Neuroplex is the one where we create the Proxy, and this DeepProbCEP is the one where we use this probabilistic logic, and you see kind of that trade-off playing out to the extent that for the kind of benchmarks we are using, currently we cannot run it on DeepProbCEP, okay? So we are limited to more simple examples because the computational complexity just kind of blows up. Having said that, there's a lot of work happening. One of my colleagues at UCLA, Guy Van de Bruyck, is doing a lot of work in this space where there are more efficient ways of representing symbolic logic and being able to learn over it to the extent that we hit neural network type efficiencies. Perhaps we are kind of on a path towards that. So the key takeaways from this far is, I think, sort of this combining neural and symbolic kind of begins to address some of the things that I kind of pointed out, while perhaps retaining sort of good part of both. For us, the motivation was these complex events, but there are a variety of other benefits that sort of accrue from it. So I want to touch upon a few other things also. So one of the things that also lets us do, and this is sort of much more recent activity, which is once we are able to structure our systems in this particular way, going back to this issue of explanation. So much of the explainability work that you see in AI is like, why is it a cat? Well, some approaches kind of paint the regions of the image. Some may point out the cat has the ear and particular whiskers or stuff like that, right? They can point out to features and things like that. When we are talking about complex events, it's a much harder thing. I have to convey things about the sequence in which things happened in order to kind of make the case. So in our recent work, what we did is that layer between the neural and the symbolic, we kind of structure the notions of time there in a particular way, and we have this system called XCAR, which attempts to exploit that information. Without going into details for our nursing activity and restaurant hygiene, these are the kind of explanations we are able to give, where we give the explanation that something is this because this happened, followed by that, or we can offer counter examples for this thing. And this is something where if you simply had kind of end-to-end DNN with LSTM or something, is just super hard to kind of even distill. We cannot map it back into semantic space. So one of the advantage of this neuro-symbolic kind of approach is that we are enforcing a semantic concept layer, but it has to be more powerful, one which captures sense of time and location. One other piece of thought line out here. So I mentioned that our ability to go between neural and symbolic has been advancing sort of quite a bit. One community which is working quite a bit in this space is people in program synthesis. Where given a specification, I want to synthesize a program, and now what if that program has neural components? So there is expeditions in computing called Neuro-symbolic, which has been exploring this issue from a program synthesis perspective. Point from our perspective is that at this point, we can take rules, train a neural network, or we can take a neural network and lift it back into rules. Of course, in both cases, there is some loss of fidelity, but at a level where we can kind of go, we can go back and forth. And this leads to sort of this notion that the space of neurosymbolic architecture is not simply the one which I presented. The one I presented, you can think of it as symbolic follows neural, right? I mean, the neural stuff gets us into some dictionary of concepts, atomic events, which are time-stamped and location-stamped, and then there is a reasoning layer. But you can imagine other also. So neural after symbolic. Now, actually, this is something that we have always done, right, in the past. In recent years, we have begun to operate on raw sensor data, but more typically, we process sensor data using some signal processing things to extract some features, and then the DNNs operate on the features. In some cases, like Tarek has some beautiful work where kind of does Fourier transforms. Other people have other types of features. So we have always done that, but now you can imagine architectures which kind of interleave these layers. At some level, what matters is the interface being symbolic and not so much what the individual modules are. Another version which plays an important role is where you take the same input, feed it into neural, feed it into symbolic, and then you aggregate or fuse them. And one common pattern that occurs out here is that symbolic gives us the approximate answer, which is the simple physics that you have, and then the neural provides the residual error. But that's one way of thinking about it. There are other ways, other roles that this combination can place. For example, in other settings, neural has the primary responsibility of coming up with the answer, and the symbolic acts as a police. So like, for example, in a deep RL setting, the neural gives the action space, but the symbolic says, is this action safe or not? And if it potentially is unsafe, it sort of corrects for it. So the whole concept of like barrier functions and control that have emerged, you can view it in this way, that sort of the symbolic is acting as a police. Another version out here is that at training time, we may want neural network to learn certain background knowledge which is symbolically expressed. So you can think of this as a way where symbolic module is acting as a regularizer in a couple of ways. One is literally you take your symbolic rules and add them as a regularization term and in our usual training paradigm. And since I mentioned logic can be differentiable, so we can play that game out here. And my colleague Guy, who I mentioned, they recently, I noticed, have a package which works with PyTorch called Pylon, which lets you essentially kind of play this game. Another approach which I've seen recently is take neural network, lift it into rules, and then examine the rules, do verification and whatnot, and after you have adjusted the rules, you can go back to the neural. So essentially, we can play this game of creating neural systems which have certain desired properties. Neurally accelerated symbolic is another pattern that we've been using, which is I have a overall first principles thing, but selective elements of it either model physics or can benefit from an acceleration, and therefore we replace them with their approximate neural counterparts. And finally, the work in recent years in Q&A, visual Q&A, you can think of it as creating computation graphs of neural models. So my outer structure is a symbolic structure, a data flow graph, except that the data graph nodes are these neural networks. So inspired by this, one of the things we kind of also did was, could we, our initial stab at complex event was creating a neurosymbolic architecture which was for a given set of complex events. What about novel complex events? If I want to throw something new at it, could I essentially learn a new set of rules or modify the existing set of rules in light of a new complex event that might have been asked? So the counterpart of this in recent years in both NLP and visual have been that I give you some data and I let you ask questions about it. So you can think questions as a form of complex event. Detect, did this happen in this text, right? Or so that's kind of the idea. So one work which we've done recently is kind of takes this approach where you look for complex events by asking a compositional question like what did the user wash hands after coming inside, stuff like that. So you can think of complex events in the form of a question, and then what we do is in our sort of following essentially the same paradigm as visual Q&A is doing, we basically create a graph of neural modules which attempts to kind of answer that. So with that, I'm going to sort of summarize some of the thought lines that sort of we have on this thing. So one is that we started this work 3 years ago or so. The logic side of this field is also advancing quite rapidly. If you look at what is happening in this space, they are fighting back with the neural side by improving efficiency, looking at different methods, recognizing hardware constraints and all. So one can potentially benefit from that. The notion of symbolic that we focused on initially was logic programs, probabilistic logic programs, but it need not be the only one. For us, the part of the interest was we were doing it in context of military applications where expressing background knowledge was very important for us, and logic programs provided a lot of benefits in that context. But physics simulators can play that role. Optimization tools can play that role, SMT solvers, and of course our good old DSP and physics, and then DSP and control theories can play that role. A third one, and this is like, we took the approach that symbols to us means categorical variables, right? The neural networks are outputting one-hot vectors with some probabilities associated with it, or they are real valued things which are like where the position is something. But it doesn't have to be that way. You could even think of if I'm taking my raw sensor data using a autoencoder to map it into an embedding vector, and then that embedding vector could be my symbol, and then I'm doing an algebra over that in the space. Spatial and temporal concepts, so having them be present at that interface between neural and symbolic is quite important. Much of what exists in the space doesn't have strong semantics, but some of the work I have seen lately where it is using things like spatial, signal transition logic, signal temporal logic, or spatially enhanced versions of those begin to play that role. And then finally, it's not simply enough to dump out, hey, I detected a complex event. We need to associate uncertainty and probabilities with it, as well as their uncertainties in their occurrence time and occurrence location. So all of these things are kind of remain open, because now you have to propagate these things across two very different paradigms. So with that, I'm going to stop. And I don't know what happened to my acknowledgement slide, but this was obviously not work just by me, actually almost none by me. It was by my students, but also my great collaborators at ARL, particularly Lance Kaplan, and a bunch of them in UK, Alan Priest's group, and so really want to acknowledge them as well. So with that, I'm going to stop, and I guess I'm ready to be grilled. So thanks.